Good morning. My name is Chris White, and I'm really pleased to have the opportunity to talk to you about durability considerations outside of photovoltaics. You may remember me from my career at NIST, and we'll be talking about some of those research. And I now am working at Exponent, and my contact information is there. Today we're going to be talking about durability and why it's so difficult. And that's because durability is not a state property. It depends on the location in which you're actually trying to make that assessment. The weather in Miami is completely different than the weather in Maine. It also depends on the specific susceptibility of the material. If you have an epoxy formulation, it's going to be very sensitive to water, whereas with polyethylene, it really is not. And quantifying durability then creates a significant drag because it takes so long to get the data. It takes so long because we essentially rely on two current historical methods. The first is long-term outdoor exposure, and the second is an accelerated laboratory or threshold-based test. All the tests really basically rely on one of these two methodologies. And there they are simplified into this table. And both of them really give an output that's pass or fail after you've fulfilled the criteria or the procedure that are there. So this, if you're a manufacturer of a new material, you essentially have to wait years to get the durability data using outdoor exposure, or without that long-term durability, you rely on accelerated testing which meets those particular standards, and that may expose you to significant liability. We're familiar with the black swan problem. This is actually the gray rhino problem, that it's charging, it's obvious, it's visible, and when it gets to you, it's going to have a large potential impact. So here are three examples of material failures that were caused by material weathering. The first one was that there was polymer stabilized rocket propellant used in the coal industry. And when the coal industry collapsed, they ended up storing 18 million pounds of this stabilized material in the heat, humidity, and UV in southeastern Louisiana in cardboard boxes in the sun. Of course, as the polymer degraded, you ended up with two very significant explosions. We're all essentially aware of what happened to the Takata airbag inflators. They had a novel propellant technology for which they did not understand the environmental degradation, resulting in the bankrupting of the company and the recall of 40 million cars. This last one is the IAC building in New York. This is where the architects borrowed design tools from different disciplines to create curvilinear surfaces for the building envelope. To achieve those curvilinear surfaces, they cold warped the insulating glass units. They basically bent them on a true, creating a static strain on the material, and then held them in place with building joint sealants. Upon the successful delivery of each new curvilinear surface building, the architects produced more and more aggressive designs, producing larger and larger static strains on the building material, creating larger strains on the building joint sealant. If they're successful at developing these curvilinear envelopes with insulating glass units, it's only a matter of time before they start asking for their curvilinear surfaces to be included in building integrated photovoltaics. One of the problems is that these static strains are not accounted for in the standard methods of durability assessment. It's difficult for the standards community to catch up for that because it's a consensus process, and everyone must be aware of it and then agree that that's a problem and then design test methods to figure out how to make that work. So that liability shield that you get from durability standards is not going to be effective if the conditions present in the exposure space are not accounted for in the standards themselves. So we need to update essentially the durability test methods and develop a new type of test method to make that work. We're very fortunate that ASTM has passed a standard that essentially lays out the procedure to develop an accelerated laboratory test. The flowchart on the right is essentially exactly how to do that. Let's just create a much simpler version of that. Here's that much simpler version. We're essentially going to start with the generation of the laboratory database, the shown there. In order to do that, what's different about this exposure chamber that was developed at NIST, the sphere, is that it's essentially at constant conditions. So what we're going to do is we're going to determine the rate constant at constant conditions, and all of those conditions are going to be equivalent to what we would see in an outdoor environment, except for the UV, and we're going to carefully model and monitor the exposure on the UV. So here are the results that we can get from that particular thing. You can see here that if you have dark and no movement, essentially nothing happens. If you turn the lights on, the rate starts to go up. And if you turn the light and the heat up, the rate really goes up. And what we do is we model that on a bunch of different conditions based on a design of experiment to get a database of exposure. And the nice thing is that all of the conditions except for UV are at directly comparable to outdoor exposure, and we have the Schwarzschild or the reciprocity rule to allow us to compare it to outdoor exposure that way. So once we have the laboratory data, we need to get the outdoor exposure. Here's the outdoor exposure at a Florida location, and what's useful about the outdoor data is that we actually measure the property change that's there and record the weather at which it was, because the value of this outdoor data is going to be in the validation. So once we have that, then we can develop our model. So here we've developed a model. This way, our model is a Bayesian hierarchical model with bootstrap sampling to allow us to calculate the standard uncertainty. So we're using the experimental data we got from the sphere to develop a materials response surface, and that's quite useful. We can use that then to generate the predictions, and the predictions we're going to do. The first prediction we want to make is see if we can actually pick up two different conditions and model that effectively. And so what we see here is two different conditions, and then we can see that the model correctly predicts the change that would occur from going from essentially a dark condition to a light condition, where we've changed not only the UV intensity, but also the movement. With that successful demonstration, we can move on to outdoor data and consider that a whole series of individual 1-hour steps. And here we can see for a 3-month exposure, the model prediction over 17 different outdoor exposures, only 3 of which are pictured here. The model prediction is the solid red line in the middle. That's the arithmetic mean, and the shaded area is the relative standard uncertainty. And you can see that we've done a good job of essentially modeling these 3 different conditions. With this model now, in the validation that we've gotten from the outdoor data, we can now move on to generalize it to any particular weather condition. And here we've picked 2,500 different locations across the United States and generated essentially how this material would change if it was in those particular locations across the United States. So it's generalizable to essentially any location where we have a weather file. So now we have this third test that allows us to do that. And we can see that the output is a database of rate constants, which we can constantly add to. And the relationship to design life is that we have a validated predictive model that is applicable to any particular weather test. So some companies have already adopted this sphere technology moving forward. The problem that they're essentially trying to solve is that they have two chemistries, one with great durability and one which is much cheaper and very paintable. What they want to do is create a hybrid sealant with the durability of one and the cost effectiveness and the paintability of two. Establishing the durability using the sphere allows them to enter a multi-billion-dollar market with a monopoly position. So the NIST approach is quite useful. It's essentially the first demonstration of the linkage between the field and laboratory for a number of different systems. Xiaohong Zhu has demonstrated it for building for photovoltaic materials as well, and she's presented that here before. And we've seen that others have adopted this technology. You do need the expensive hardware of the sphere to adopt this method, and it's not yet standardized because it has not seen broad adoption. And all the examples that are brought forward and demonstrated are designed to rapidly degrade. A potential new approach to durability comes from the folks at Exponent, and that's in the concept of using fragility curves. Essentially, we start with a large database of very similar items, all with essentially different exposures. And then what we would do is take all of those exposures and use them to create the database in which we could apply Bayesian statistical methods to develop fragility curves to estimate the probability of failure of each individual asset. The example I'm presenting is for Pacific Gas and Electric. We're looking at their asset failure as a function of wind speed. So what PG&E has is that they have a huge number of steel towers and wooden poles and other assets. And for each one of them, they know what the condition is and they know the exposure history. Those essentially become the inputs to the database. And here you can see we can develop fragility curves based for each individual steel tower or wooden pole. Here is a steel tower where the condition is actually corroded some, and you can see that the performance of the steel tower as a function of wind speed is actually lower because of the corrosion. For the wooden pole example, you can see by adding guy wires to the pole, the remediation, that we can actually increase the reliability as a function of wind speed. So now as the wind speed goes up, you can estimate the probability of failure and essentially decide when to shut down the grid. The nice thing is that this particular approach allows us to essentially generate the data from a utility scale solar installations where every single panel becomes an input into the database that allows us to predict how any particular panel would do. We could also build that database from exposure conditions, and we could do it out of any building envelope because each insulating glass unit is going to be an entry into the database. The nice thing is that we can generalize this to all other installations once we have the model and the validation. And every time you run the model, you actually get new components and the database gets bigger and the predictions get better. So now we essentially have these four different ways of calculating durability. And if you're interested in understanding more about fragility curves, please talk to me after the session. And we can see that both the two Bayesian statistical methods allow us to essentially have predictive models with known uncertainty. So the question is, why should we care about durability? And I would argue that the landscape for durability is changing. And that's essentially coming from this investor pressure from people like Michael Bloomberg, who've created the task force on climate-related financial disclosures. And what they're essentially demanding is that in order for this large group of investors to invest in your company, publicly traded company, you have to disclose the downside risk associated with condition assessment. And essentially all companies in the United Kingdom are required to comply with this by 2025, and the US regulators are right behind. So those are investors. There's also this idea of the Scope 3 standard, which is a disclosure of the total embodied energy across the entire value chain. Like the TCFD, the Scope 3 standards allows you to have or requires you to know the durability of all of your assets. For example, if you produce two solar panels and they take the same amount of energy to produce, but one has a different durability, the Scope 3 reporting panel for the longer durability material is much lower, and you can actually command a higher price. How does it actually work in practice? If you look at a company like Assa Abloy, they make metal door hardware, right? So why would a metal door hardware company be concerned about sustainability and durability? It turned out because they didn't quantify what that was, they were essentially locked out of contract bids all across Europe. So they created a sustainability division and secured the certification documentation of what the embodied energy was and the durability of theirs. And they essentially took the same hardware, put it in different boxes with this additional piece of information, and created the fastest growth across the multi-billion-dollar company. So the understanding is that consumers will demand that transparency and sustainability calculations, which require accurate durability assessments across a whole spectrum of goods and services, both the Scope 3 standard and the TCFD requirements. Understanding these requirements is something that a lot of people are struggling with. For example, the United Nations just ran a pilot program with a number of banks in the United Kingdom to help them figure out how that they would address the TCFD requirements and also the Scope 3. And they found that the existing tools don't work very well, and they were specifically lacking in the ability to assess the characteristics of individual assets, age, and condition, which is exactly what we were able to do at Exponent using the fragility curve approach to make that happen. So just to wrap up, durability is very hard to measure. There are two historical methods that we've covered, and they really don't provide predictive models. We've talked about two new methods that employ Bayesian statistical methods, both of which provide validated predictive models. The NIST approach says we're going to build a database of rate constants, and then by monitoring these essentially constant exposure and build a materials response service to make that work. The exponent approach that I've outlined essentially says we're going to collect a database based on a survey of existing exposed elements and their known exposure history, and then we're going to apply our Bayesian statistical methods to generate fragility curves and move that forward. Again, if you're interested in understanding how to make that work for other installations, please contact me and we'll make that happen. I'd also like to argue that the market for durability assessment is changing, and it's changing rapidly, and that's due to pressure from investors, regulators, and also consumers, and they're all beginning to require accurate durability assessments. And with that, I'd like to stop. And again, I'm Chris White, and here's my contact information, and I look forward to answering your questions at the break.